Welcome to JEE Concept Galaxy. Hit that like and subscribe button as we dive into a high-energy explainer on the absolute fundamental rules of the universe, Newton's laws of motion. Whether you are encountering these for the very first time, or you're deep into your JEE Advanced preparation, these laws are the bedrock of classical mechanics. So, get ready to seriously upgrade your physics intuition.
So let's kick things off with a fundamental question to really test your intuition. Do you actually know what causes a body to speed up, slow down, or even just change its direction? It sounds incredibly simple, right? But for centuries, brilliant minds thought that objects naturally came to rest and needed a constant push just to keep moving. It wasn't until Galileo and then Isaac Newton that we realized the truth. A change in speed, or even just a sideways change in direction, requires a specific active influence.
Here's our roadmap for today's explainer. We're going to cover 1. The concept of force. 2. First law and inertia. 3. Second law and momentum. 4. Third law, action and reaction. 5. Inertial frames. And finally, 6. Applying Newton's laws.
Section 1. The concept of force. Okay, let's dive into this first section and establish exactly what a force is before we start writing out any complex equations. In physics, forces are vector quantities, meaning they have both magnitude and direction. And they essentially come in two flavors. First up, we have contact forces. These exist only as long as objects are physically touching each other. Think of the normal force from a table pushing up on a book, the friction slowing down a sliding block, or the tension in a stretched string. Second, we have non-contact forces. These act over a distance without any physical connection whatsoever, like the gravitational force pulling you toward the Earth, or electrostatic forces between two charges.
Section 2. First law and inertia. This formalizes something Galileo originally discovered, which Newton then polished into his first law.
Newton's first law, often called the law of inertia, states that a body simply will not change its state of rest or its uniform straight-line motion unless an unbalanced external force compels it to. Inertia is literally just this stubbornness. It is the inherent property of a body to completely oppose any change to what it's already doing. And here is a crucial takeaway for your prep. The inertia of a body is directly measured by its mass. The more massive a thing is, the harder it is to get it moving, or to stop it once it's going.
And this perfectly explains so many everyday phenomena. Have you ever wondered why mangoes drop when you shake a branch? Well, the branch moves, but the mango's inertia of rest keeps them stubbornly in place, snapping the stem. Or why you lurch backward when your bus suddenly accelerates. Your lower body moves forward with the bus, but your upper body wants to stay exactly where it was. And when you beat a blanket with a stick, you're just moving the blanket out from under the dust particles, which simply hover for a split second before gravity takes over. It's all inertia.
Section 3. Second law and momentum. Let's see how this builds into the critical mathematics of mechanics. This is where we put actual numbers to the concepts.
But first, we've got to clear up a major confusion. As the legendary physicist Richard Feynman pointed out, do not confuse your weight with your mass. Mass is your inertia, literally how hard it is to get you moving. Weight, on the other hand, is just the local gravitational pull on that mass. If you take a spaceship to Mars, your weight changes completely because Mars has much weaker gravity, but the force required to shove you across the floor to overcome your mass stays exactly the same.
Before we can even define the second law, we absolutely have to grasp the concept of momentum. Think of momentum as how much oomph a moving object has. It's the product of an object's mass and its velocity. A heavy truck moving slowly can have the exact same momentum as a tiny bullet moving incredibly fast.
So here's the crucial point for Newton's second law. Force is the time rate of change of momentum. If an object is changing its momentum, whether that's speeding up, slowing down, or turning, there absolutely must be a net force acting on it. Mathematically, if the mass of the object isn't changing, this brilliant law simplifies to the most famous equation in mechanics, F equals ma. Force equals mass times acceleration.
Section 4. Third law, action and reaction. Now, this one is widely quoted in pop culture, but honestly, it is so frequently misunderstood by students in the exam hall.
A massive misconception we need to bust right now is that action and reaction forces somehow cancel each other out. People always think, well, if every force has an equal and opposite force, how does anything ever move? The reality is, they never cancel each other out because they are applied to completely different objects. They're an interaction between two totally distinct bodies. Think of it this way.
If you kick a ball, your foot pushes the ball forward, but the ball pushes back on your foot. If a book rests on a table, the book pushes down on the table while the table pushes up on the book. And get this, if the Earth exerts a downward gravitational pull on a falling particle, that tiny particle is simultaneously pulling the entire Earth upward with the exact same magnitude of force. The Earth's acceleration is just unnoticeably small because its mass is so unimaginably huge.
Section 5. Inertial frames of reference. Okay, so all of this sounds perfectly logical, but do these laws apply identically everywhere? Like, can you use F equals ma whether you're sitting at a quiet desk or riding on a wildly accelerating roller coaster?
Well, the short answer is no. Newton's laws only strictly work in an inertial frame of reference. An inertial frame is just a viewpoint that is either totally at rest or moving with a constant velocity. If your frame of reference is accelerating, like if you're on a spinning merry-go-round or in a braking car, Newton's first law appears completely broken. Objects seem to just accelerate without any real forces pushing them. Therefore, the first law acts essentially as a test to determine if your viewpoint is even valid for using the second and third laws.
Feynman perfectly illustrates this concept of Galilean relativity. Imagine a child bouncing a ball in a smoothly flying airplane cruising at a constant 500 miles per hour. The physics look exactly the same to that child as if they were bouncing it on solid ground. As long as the velocity is uniform, the laws of mechanics are totally identical.
Section 6. Applying Newton's laws. Now for the grand finale. Let's bridge all this beautiful theory into some hardcore application for your JEE exam prep. How do we actually solve problems?
When you're attacking multi-block pulley systems, your absolute best friend is the free body diagram. You must mentally isolate every single mass. And here's a pro tip, straight from H.C. Verma's concepts. The action-reaction pairs from Newton's third law will never, ever appear in the same free body diagram. Because remember, they act on different objects. You draw the tension pulling up on block A and gravity pulling down on block A. You set up F equals ma for block A, then you do it all over again for blocks B and C.
And what about inclined planes? When you're dealing with these setups, you need to immediately isolate the components of gravity. The force of gravity pulls straight down, but you've got to resolve it into vectors parallel and perpendicular to that slope. You apply the F equals ma equation to each mass individually, track the tension forces connecting them, and solve the simultaneous equations to find the entire system's acceleration. It is all about breaking complex systems down into individual, manageable pieces using Newton's rules. I'm going to leave you with this final, vital puzzle to test if you've truly mastered today's explainer. Drop your answers in the comments section. If a book on a table is pushed up by the table's normal force and pulled down by the Earth's gravity with an exactly equal force so it doesn't move, why isn't this an action-reaction pair? Think really carefully about the bodies involved. Thanks for tuning into this explainer on JEE Concept Galaxy. Keep practicing those free body diagrams, and I'll catch you in the next one.